The last major thing we need to look at in the forces and fields unit is again an application of sort of the theory that we've looked at over the last little bit. And this has to deal with the mass spectrometer. If you've taken chemistry, especially IB chemistry, you would have talked about the mass spec in a fair bit of depth. We actually don't really need to know a lot of depth about it. We're more interested in the physics of what's going on, not necessarily the actual mechanisms of what are going on in here. Now, the mass spec, I will explain just what's going on, because hey, if you also happen to be doing IB chemistry, we'll kind of kill two birds with one stone on this. But first thing that's going to happen is your chemical is going to get broken down into its respective elements, and then what's going to happen is we need those elements to become ionized, because neutral particles, they're not going to be affected by electric and magnetic fields. So we're not going to build this whole contraption to look at particles and then not be able to use it with a neutral particle. So what's going to happen is they're generally going to be bombarded, our sample, we're going to bombard it with high-speed electrons. What's usually going to happen is we're going to knock off some of those valence electrons in our sample, then it's going to become ionized, and then once it's ionized, well, we can start to have some effects with electric and magnetic fields. So, if you have your sample here, there's the nucleus, there's our, our shells. Let's say we have this electron in the valence shell here, and then I have this other nice little happy electron kind of coming along. Well, what it can do is it can kind of come in, they can collide, and then it can knock this electron out. This thing becomes ionized now, and now it'll be affected by electric and magnetic fields. So every mass spec is a little different, but generally what's going to go on here is so they're going to get ionized in this chamber, and then we're going to pass these ions between two parallel plates, and they're going to be accelerated. So between these two parallel plates, we're going to have a potential difference. Usually in here, we're just going to have electric fields only. And as you've seen already, when we're dealing with these cases of kind of the two parallel plates where the particle's traveling directly from one plate to another, these are pretty much just begging for conservation of energy, or physics principle number 5. Now, once we get the particles out of here, they're going to go into what's called the velocity selector. So we're picking specific particles that we'd like. Generally in here, we're going to have both electric and magnetic fields. Most likely what's going to be going on here is that the particle is going to be undeflected. So you'll notice that it's traveling in a straight line. This also means that the magnetic force and the electric force, they're balanced in this region. If they're balanced, we know if the net force acting on something is 0, we know that this is just going to be uniform motion, or physics principle 0. There's an equation, we'll look at it in a little bit. We know in a velocity selector, if the magnetic force and the electric force are balanced, there's this equation that we can use, V equals E over B. So we can use the electric field strength divided by the magnetic field strength. But we've got to be really careful with that equation. That equation is a very special case, and we can only use it in that specific context. After the particle sort of makes its way out of the velocity selector, we're going to turn off the electric field. So then we're going to get it into this region where we have the detector. At this point, we're just going to have the magnetic field only. Now, the magnetic field can't do any work, so it can't change the speed of the particle. So once the particle exits this plate, whatever speed it happens to have, that speed is going to be constant. Now, the velocity does change because the direction's changing, but the speed will not change between the velocity selector and the detector. We also know that once a particle enters a magnetic field, it will undergo circular motion. And then usually what's happening in a mass spec is you'll have different isotopes of different samples. They'll have different masses, they'll have different radii of curvature, and then depending where they hit on the detector, that can give you an idea of what specific isotope of a sample you have, and then you can look at its abundance in a chemical sample. These mass spec questions, they're absolutely excellent on the diploma exam. because they could cover a wide variety of curricular outcomes. You could easily have about 10 of 50 questions on the diploma be a mass spec. So be ready for them. We're going to look at a couple of examples. So we're going to start with one right away here. Sometimes you get a picture, sometimes you don't. It just depends on what's going on. And what I have here is I have what we'd call a double numerical response. As you know, on the diploma exam, the last two questions on the exam, numerical 13 and 14, is going to be a challenging calculation. Numerical 13 will ask you to make the calculation. Numerical 14 is going to ask you to identify the physics principles that you used in the question. So let's have a look at this one. So we have a singly charged ion, and it's passing undeflected through a velocity selector of a mass spectrometer. We're told that the magnetic and electric fields in the velocity selector are perpendicular to each other. That's good. That'll make sure that the forces of the two fields will be able to counteract each other because they'll be in the same plane. The magnetic field strength is 0.25 teslas, and we have an electric field strength of 7.0 times 10 to the 3 volts per meter. These ions then enter the separation region where the magnetic field strength is the same as in the velocity selector, because again, magnetic field can't change the speed. So the radius of the deflected ions is 8.1 times 10 to the minus 3 meters. What we're being asked for is we're asked to find the mass of this singly charged ion. Right, we have two things that are going on in here. First of all, we have the velocity selector. So in the velocity selector, this particle that we have, it's going to be undeflected. That's what we've been told. So we know that the forces are balanced in here. Once it gets out of the velocity selector, it's going to end up in a detector. So again, pardon my very crude drawings here. They're not that great. But, you know, eventually it's going to end up in a detector, and it's going to undergo circular motion. So in my velocity selector, we have electric and magnetic fields. In the detector, we're just going to have magnetic fields only. Excuse me. Now, let's have a look at this. Because if we want to look at the detector, we're going to need the velocity, or we're going to need the speed from the velocity selector. But to get that, we kind of have to look at the velocity selector first. So we're going to start in the velocity selector. Now, in the velocity selector, we haven't been told anything about the direction of the magnetic force and the electric force, but since it's undeflected, we know they have to be in opposite directions to one another. What that happens to be, whether the FE is up or down, and then FM is down or up, it doesn't matter. What's important is that they balance each other out. So for my free body diagram, I don't know, I'll just make the assumption that FM's going up. Why not? And then if it's going up, FE has to go down by default. You could draw this with FE up, FM down. It won't matter since the net force is 0. I will call the up direction positive. So we can write our net force statement. The net force is just going to be the magnetic force plus that electrostatic force. And since it's undeflected, well, good news is we get to get rid of this term right away, since it's undeflected. So we know that this 0, this is going to be the magnetic force plus that electric force. Or we know that 0, this is going to be QVB plus QE. What we can do is we can solve this for V, or I can put things on other sides, so I can say that QVB, this is going to be negative QE. Now the charge, that's going to go away. Or sorry, I shouldn't have crossed out velocity. The charge is going to go away, so I'm going to keep that V there again. We're going to get rid of that charge. So I'm going to have this VB is equal to negative E. Now, we don't really want that negative there, because again, we're dealing with vector fields, but since I'm specifically looking at magnitudes, I can pretty much ditch that negative sign there, because this is all just coming from directionality. So we're going to ignore that negative, since we're just looking at magnitude only. Some of you would have probably written this, instead of avoid that problem, you would have kind of embedded your negative in FE. So you would have written FM minus FE, and that's fine too. I've just found that trying to switch notations, it causes students confusion. So I'm going to go with this. I'm going to go with V equals E over B. Again, don't worry too much about that negative sign there. So we know our electric field strength. We're told it's 7 times 10 to the 3 volts per meter. And then we're told field strength is 0.25 Teslas. So this is going to give us about 28,000 meters per second. Sig digs, don't worry about it too much right now. So we're going to get that the speed of this particle when it enters the velocity selector. It's about 28,000 meters per second. This is the speed that the particle is going to enter the detector with. So this is V in the detector. Now we want to start to focus our efforts on the detector itself. So we're going to move from the velocity selector, and we're going to move to the detector. So in the detector, we know that this particle is going to undergo circular motion, so we know that the centripetal force is going to be provided by the magnetic force, or we know mv squared over r. This is going to be qvb. So we don't want this v. We can get rid of that v squared, get rid of the square, we can get rid of one of the v's. So I'm left with mv over r equals qb. Well, the objective here is to determine that mass. So we know Q, we know B, we've been given R, we've just found V. So this is from velocity selector. We're just going to rearrange this for the mass. So the mass is going to be this QBR divided by this V that we've already determined. So the last big step in all this, plug it all in. So we've been told it's singly charged, so we know the charge is 1.60 times 10 to the minus 19 coulombs. Magnetic field strength, we haven't been told it changed, so we're still going to, so it's 0.25 Teslas, and this radius, about 8.1 times 10 to the minus 3 meters. Then we're going to divide that by that lovely velocity we just found. So if we did that, we're very careful, we're going to get about 1.2 times 10 to the minus 26 kilograms. Since the lowest number of significant digits I have is 2 from the magnetic field strength and the radius, we're going to write this in 2 significant digits. So I get 1.2 times 10 to the minus 26 kilograms. Looking at the question, it's asking for this in the form A dot B times 10 to the minus CD. So we got 1.2 times 10 to the minus 26 kilograms. So if we were to fill this in the box, we get 1226. Now again, this is a great numerical response question because you have to understand we used quite a few equations in this to get our mass. And you should expect for a double numerical response, you should expect to use anywhere between 3 and 5 equations on the data sheet in order to get your answer. Now the last part has to deal with the physics principles. So the physics principles, usually I always recommend to my students, if you have a real hard time with the calculation, at least take a guess at the physics principles. You may surprise yourself and get the physics principles right. Numerical 13 and 14 are each worth 1 mark, so if you don't get the mark for the calculation, at least take a stab at the mark for the physics principles. So the fact that this particle is undeflected, when it's undeflected, these are balanced forces. So this area in the velocity selector, that is physics principle 0. That is uniform motion. So we use this first. In the detector, We have Fc equals Fm. We're talking about circular motion. The moment we see charged particles and magnetic fields, this is going to be circular motion. So in this problem, we've used physics principle 0 and physics principle 2. Now you've noticed, you've probably seen this, your teachers have likely explained this to you. We have this used first and used second. Now we did use them in the order of 0 and then 2. On the diploma exam, the order actually doesn't matter. They don't care the order that you use them. What they are really asking you is what are the 2 physics principles you used, not the order. So the other answer that would be accepted in this case is 2-0. They're both going to get marked right, so don't spend a lot of your time stressing, oh, which one did I use first and then which one did I use second. Just identify the 2 that you used. Order doesn't matter.